Magma is the molten rock beneath Earth's surface. It originates primarily through partial melting of pre-existing solid rock within the crust or upper mantle. This process rarely involves complete melting. Instead, specific minerals with lower melting points liquefy first. Three key mechanisms trigger melting by reducing the melting temperature of rock. The first mechanism is decompression melting. As mantle rock ascends, for example at mid-ocean ridges or mantle plumes, pressure decreases while temperature remains high. This crosses the rock's solidus, or melting curve, causing partial melting. This is the dominant process generating basaltic magma under oceanic ridges and hotspots. The second mechanism is flux melting. The addition of volatiles, primarily water, but also carbon dioxide, significantly lowers the melting temperature of mantle peridotite. This occurs when water-rich fluids released from a subducting oceanic slab infiltrate the overlying hot mantle wedge at convergent plate boundaries, producing hydrous magmas like andesite. The third mechanism is heat transfer melting. Hot magma rising from the mantle can transfer sufficient heat to melt surrounding crustal rocks. This is common in continental settings, leading to the formation of granitic magmas, a process also called anaxis. The initial composition of the magma is dictated by the source rock composition and the degree of partial melting. Melting mantle peridotite typically produces mafic, or basaltic, magma rich in iron, magnesium, and calcium, but low in silica and potassium. Melting continental crust produces felsic, or granitic, or rhyolitic, magma rich in silica, aluminum, sodium, and potassium. Low degrees of partial melting yield magmas richer in incompatible elements, such as potassium, uranium, thorium, and rare earth elements. Magma evolution, also called magmatic differentiation, describes how the composition changes after initial formation, primarily through processes occurring during ascent and storage within magma chambers. The first process is fractional crystallization. As magma cools, minerals crystallize. If these crystals separate from the remaining melt, for example by sinking due to density or being trapped along chamber walls, the melt composition changes. The sequence of crystallization is described by Bowen's reaction series. Early crystallization of dense mafic minerals like olivine and pyrrhozine removes magnesium, iron, and calcium, enriching the residual melt in silica, sodium, potassium, and aluminum, driving it towards intermediate and felsic compositions. This is a dominant process in large magma bodies. The second process is assimilation. Hot magma can melt and incorporate surrounding wall rock, also called country rock. This contaminates the magma, altering its composition depending on the nature of the assimilated material. The third process is magma mixing. Magmas of different compositions, potentially from different sources or stages of evolution, can physically mix within the crust, creating hybrid compositions. The viscosity of magma, crucial for its eruptive behavior, is strongly controlled by temperature and composition. Higher silica content and lower temperature increase viscosity. Mafic magmas are hot and fluid, meaning they have low viscosity. Felsic magmas are cooler and sticky, meaning they have high viscosity. Density contrasts between magma and country rock, coupled with pressure from below, drive ascent via fractures called dikes, or by displacing or blasting overlying rock, a process called stoping. Magma that solidifies underground forms intrusive rocks. Eruption forms extrusive rocks. This video about magma formation and evolution is part of our larger Geology for Environmental Science students course. The course is entirely free and has more than 100 subtopics inside it. We're excited for you to try it, and the link is in the description.